All right, so we're going to briefly talk about the spring force now, simply because we're going to be using it in some problems when we start talking about centripetal force and some other things. So just get a little bit of an introduction. We'll talk more about springs later. But to start, an ideal spring has negligible mass and exerts a force that is proportional to the change in its length, as measured from its relaxed length. So you've got a spring, and it's got its relaxed length. That means when there's nothing pushing or pulling on it, this is the length of the spring. So let's say that's my spring, and that's its relaxed length. Okay, so nothing's pushing or pulling on it. It's not stretched. It's not compressed. And the force that we could find, the spring force, would be proportional to how much we then compress or stretch it. So let's say we take it and we compress it, we smush it all together. So we still have those three little coils, okay, but we smush it together. That force that is now in the spring that it can push out with is going to be proportional to how much this length changed by. So it's not the new length we're looking at, it's how much it changed by, how much we compressed it, or if we stretch it out, okay, then we would be looking at how much we stretched it. Okay, so that's one thing to be careful of when you look at the equation for the force for the spring. You want to be looking at the change, so how much the spring's length changed from its relaxed, how much it stretched, or how much it compressed. The magnitude of the force exerted by an ideal spring on an object is given by Hooke's law. So you have the X now. What the heck is this K? The K is the spring constant. And the spring constant represents the stiffness of a spring. So on the top of my pen, that spring that's in there that I push down on, very small spring constant, because again, I can do it with my thumb, it's very easy. Okay? Whereas the shocks on your car, my thumb is doing nothing. If I take that out and try to push on it, no. Okay? It's just not enough to stretch or compress it at all. Okay? So you've got your spring constant. The bigger the number, the stiffer the spring is. Then again, X is the distance it's stretched or compressed. And then we've got the force. And it's the force is always directed toward the equilibrium position. So here's my equilibrium. So here the force would be directed that way. I'd be pushing to get back to equilibrium. Here the spring would be pulling to get back to equilibrium. Okay? But it's always going to be going towards the equilibrium position. And in this equation, there's a negative. Sometimes you can leave it out. You really have to look at the direction later on. But in the equation, there is a negative, and that's because the spring force is always in the opposite direction of the applied force. So I had to push it this way to apply force that way. The spring force is going the opposite way. When I stretch this out, now the spring force is pulling it back. Okay, so this is just a little brief introduction to spring force. We will talk more about it as we need to.